There's a hidden force at work across the universe, one that flings particles to nearly the speed of light, bending the rules of physics as we know it. These cosmic accelerators aren't just rare anomalies. They're the engines powering some of the most spectacular phenomena in existence, from black holes devouring stars to quasars shining brighter than entire galaxies. But what laws govern these titanic forces? For decades, scientists have pieced together clues, uncovering truths that challenge everything we thought we understood about space and time. Today, we're pulling back the curtain on 35 revelations that rewrite the story of the cosmos, each one a leap toward answering the big question: how does the universe really work? Strap in, this journey will change the way you see the stars. Deep in the heart of space, an invisible web of magnetic fields stretches across the cosmos, silent, unyielding, and unimaginably powerful. These aren't just passive lines on a diagram. They're dynamic forces that twist, snap, and unleash energy like cosmic whips, hurling particles to nearly the speed of light. Picture a supernova remnant, a chaotic debris field where dying stars explode. Here, magnetic fields don't just linger, they act like particle slingshots, accelerating matter with jaw-dropping efficiency. But the real magic happens during something called magnetic reconnection, a process where tangled field lines suddenly snap and reconnect, releasing explosive bursts of energy. It's like a rubber band stretched too far, finally breaking and flinging everything nearby forward with unstoppable force. This isn't just theory. Scientists have watched it unfold in space, proving that these magnetic explosions are one of the universe's most efficient particle accelerators. And if you think that's wild, wait until we see how black holes weaponize this phenomenon. Their jets, blazing beams of matter shooting thousands of light years into space, are sculpted by these same magnetic forces. It's a reminder that even in the darkest corners of space, magnetism writes the rules of motion. Imagine a cosmic fire hose blasting superheated matter across thousands of light years, relentless, focused, and unimaginably powerful. That's the reality of black hole jets, nature's ultimate particle accelerators. These jets don't just drift lazily through space. They erupt with precision, channeling energy so extreme it defies earthly physics. And at their core lies a secret: the spin of the black hole itself. As matter spirals into the black hole's accretion disk, it doesn't just vanish, it gets caught in a whirlpool of magnetic chaos. The black hole's rotation twists these magnetic fields into tightly wound coils, launching particles outward at nearly light speed. The Event Horizon Telescope has captured this phenomenon in action, revealing jets so energetic they outshine entire galaxies. But here's the twist: these jets aren't random. They follow a hidden pattern, a cosmic recipe for acceleration that repeats across the universe. From tiny stellar black holes to monstrous supermassive ones, the same forces are at work. It's as if space itself has a rulebook for how to hurl matter across unfathomable distances. And the more we learn, the clearer it becomes. Black holes aren't just destroyers. They're creators, shaping the universe in ways we're only beginning to grasp. Now, if you think magnetic fields alone are responsible, prepare for a curveball. There's another player in this cosmic dance, one just as vital and far more unpredictable. It's the hidden force that twists, churns, and supercharges particles in ways even Einstein couldn't have imagined. The secret: chaos itself. Here's the next segment, following naturally from the previous content. Think of the universe's most violent storms, not rain or wind, but vast oceans of churning plasma, swirling with enough energy to bend space itself. This is cosmic turbulence, and far from being random chaos, it's one of nature's most ingenious particle accelerators. Inside interstellar clouds and galaxy clusters, these turbulent currents collide, creating shock waves that ram particles to staggering energies. It's like a cosmic version of a surfer catching the perfect wave, except here, the waves are made of superheated gas and they propel matter to nearly the speed of light. Scientists once assumed only cataclysmic events like supernova or black hole mergers could generate ultra-high-energy cosmic rays, but turbulence offers a quieter, more widespread explanation. Picture plasma swirling like cream in coffee, only instead of mixing smoothly, it fractures into violent eddies. Each twist acts like a miniature slingshot, flinging particles outward in unpredictable bursts. Advanced simulations reveal these chaotic motions can amplify energy just as efficiently as any black hole jet, just on a different scale. What's truly groundbreaking is how this reshapes our search for cosmic ray origins. For decades, researchers chased elusive high-energy sources scattered across the sky. Now, turbulence suggests the answer might be hiding in plain sight, woven into the fabric of space itself. And if this process sounds familiar, that's because it mirrors something we see closer to home, Earth's own auroras, where turbulent solar wind sparks dazzling light shows. The universe, it seems, loves recycling the same spectacular tricks, but turbulence isn't working alone. There's something even more mysterious lurking in these chaotic currents, something invisible, untouchable, and yet undeniably powerful. It's the shadowy architect behind many of these energetic dances, dark matter, and its role might rewrite everything we know about cosmic acceleration. Here's the next segment, seamlessly continuing the script while introducing new insights with fresh energy. We've chased cosmic accelerators from black hole jets to turbulent plasma storms, but the most enigmatic player might be hiding in the darkness itself. Dark matter, that invisible scaffolding of the universe, could be pulling strings behind the scenes, shaping how particles reach mind-bending speeds. Unlike the violent chaos of supernova or the magnetic fury of quasars, dark matter's influence is subtle, ghostly, and utterly transformative. Picture a vast, unseen halo wrapping around a galaxy like a spiderweb. Most of its mass is dark matter particles that barely interact with light or ordinary matter. Yet when these particles occasionally collide, some theories suggest they could annihilate each other, releasing bursts of gamma rays or even high-speed particles. It's like an invisible fireworks show, silently energizing the cosmos. Experiments like the Alpha Magnetic Spectrometer aboard the International Space Station are scanning for these telltale sparks, hunting proof that dark matter isn't just passive, it's an active architect of acceleration. But there's another twist. Dark matter's gravity might act as a cosmic funnel. Its halos could bend the paths of speeding particles, steering them into dense clusters where they gain even more energy. Think of it as a galactic pinball machine, with dark matter's invisible bumps nudging particles to ever higher velocities. If proven, this would mean our maps of cosmic accelerators are missing half the blueprint, the shadow half. The hunt for answers is far from over, but one thing's clear: dark matter isn't just a placeholder in equations. It might be the unseen hand sculpting some of the universe's most extreme particle highways. And as we piece together its role, we're forced to ask, what other invisible laws are we still blind to? Speaking of extremes, there's another cosmic wonder where acceleration physics gets pushed to the limit: neutron stars. These ultra-dense remnants of dead stars don't just defy gravity. They warp the very rules of energy, creating laboratories more extreme than anything we could build on Earth. At the heart of some of the universe's most brilliant light shows lie neutron stars, cosmic powerhouses packing the mass of a sun into a city-sized sphere. Their surface gravity is so intense it crushes atoms into a sea of neutrons, while magnetic fields trillions of times stronger than Earth's turn their surroundings into a particle accelerator unlike any other. Unlike the chaotic turbulence of plasma storms or the shadowy whispers of dark matter, neutron stars operate with terrifying precision, firing beams of radiation like celestial lighthouses. Take the Crab Nebula, a supernova remnant lit up by a spinning neutron star at its core. This pulsar whips around 30 times per second, flinging charged particles outward in a high-speed wind. The result, a glowing nebula radiating energy across the electromagnetic spectrum, from radio waves to gamma rays. What's astonishing isn't just the brightness, it's how these particles reach such extreme energies without ripping apart. Current models struggle to explain the sheer efficiency of this acceleration, suggesting gaps in our understanding of magnetic reconnection and shock waves. But neutron stars have another trick, their magnetospheres. Imagine a tornado made of magnetic field lines, spinning so fast it rips electrons from the star's surface and launches them into space at nearly light speed. These particles then collide with slower moving matter, creating cascades of energy that illuminate entire nebulae. It's a natural particle collider operating on scales no lab on Earth could replicate, and a goldmine for physicists studying extreme conditions. Yet for all their ferocity, neutron stars are just one piece of the acceleration puzzle. Their violent birth in supernova explosions hints at an even grander source of cosmic rays, one where the death throes of a star become the spark for new particle odysseys. A star's death isn't just an ending, it's a cosmic rebirth, a moment when unimaginable energy floods the void, forging the building blocks of the universe itself. Supernova don't just fade away, they leave behind storms of raw power, shock waves rippling through space at millions of miles per hour. These violent expansions aren't just remnants, they're particle factories, churning out cosmic rays with energies dwarfing anything we could produce in labs on Earth. Take Cassiopeia A, the shattered corpse of a star that exploded centuries ago. X-ray telescopes have peeled back its chaotic layers, revealing shock fronts where particles ricochet like pinballs, gaining speed with each collision. This is Fermi acceleration in action, a process where charged particles bounce between magnetic fields trapped in the shock wave, surfing its energy to extreme velocities. It's not luck, it's physics. Each crash acts like a cosmic trampoline, propelling particles closer to light speed. But here's the puzzle. While supernova can explain much of the cosmic ray influx we detect, there's a break in the pattern, an oddity scientists call the NI. At a certain energy threshold, the number of high-speed particles drops sharply, as if something out there is capping nature's accelerator. Some theories point to shock waves losing steam, while others suggest an entirely new class of cosmic engines taking over. One thing's certain, supernovae are more than just fireworks. They're fundamental to the story of how matter moves through the cosmos, seeding galaxies with particles that might one day spark new stars or even life. And as we piece together their role, we're forced to confront an even bigger question. What lies beyond the NI? The answer could rewrite our understanding of the universe's most powerful engines. Speaking of thresholds, there's another enigma lurking in the cosmic ray spectrum, one so extreme it defies all conventional explanations. These are the ultra-high-energy cosmic rays, and their origins might lie not in our galaxy, but in the deepest voids of space. Somewhere in the vast spectrum of cosmic rays lies a mysterious threshold, a point where the rules seem to shift without warning. Scientists call it the NI, and for decades, this abrupt drop-off in high-energy particles defied explanation. Picture a cosmic conveyor belt steadily delivering particles from sources like supernova until suddenly, at around 1 quadrillion electron volts, the supply drops sharply. It's as if the universe itself has hit a speed bump, and unraveling why could redefine our understanding of galactic boundaries. Recent breakthroughs suggest the NI isn't just a random quirk, it's a cosmic border crossing. Below this energy, particles likely come from within our own galaxy, accelerated by shock waves from dying stars. But beyond it, the particles are too energetic for even supernova to produce, hinting at something far more exotic at work. Some theorists point to extragalactic sources, perhaps active galaxies or colliding galaxy clusters, flinging particles across intergalactic space like interstellar artillery. What makes this discovery so groundbreaking isn't just the energy shift, it's the implication that we're glimpsing the edge of our galaxy's influence. The knee might be a literal frontier, marking where local accelerators max out and distant, unimaginably powerful forces take over. Telescopes like the Pierre Auger Observatory are now mapping these ultra-high-energy particles, tracing their paths back to potential sources beyond the Milky Way. Every detection is a clue in a cosmic detective story, one that could rewrite the map of particle origins, yet for every answer, new questions emerge. If extragalactic sources are flooding us with these extreme particles, how do they survive the journey? Intergalactic space isn't empty. It's filled with dilute gas and magnetic fields that should sap their energy over millions of light years. The fact that they reach us at all suggests an acceleration mechanism even more efficient than we've imagined, one that might involve the universe's most fleeting and violent phenomena. And speaking of violence, nothing in the cosmos matches the raw, concentrated fury of gamma-ray bursts. These blink-and-you'll-miss-it explosions unleash more energy in seconds than our sun will emit in its entire lifetime, and they might just hold the key to the universe's most extreme particle accelerators. In the darkest corners of the cosmos, a single flicker can outshine the combined light of 1 billion galaxies for just a heartbeat. Gamma-ray bursts are the universe's most violent tantrums, unleashing more energy in seconds than our sun will emit in 10 billion years. But these aren't just flashes in the cosmic dark. They're particle accelerators on steroids, catapulting matter to energies so extreme they defy conventional physics. At the heart of a GRB lies chaos incarnate, a newborn black hole or magnetar, spinning furiously as it devours its dying star. This death spiral triggers twin jets of plasma, screaming outward at 99.99% the speed of light. Inside these jets, particles don't just move fast, they're turbocharged by internal shock waves, colliding with such violence that they emit gamma rays like cosmic distress signals. What's staggering isn't just the raw power, but the precision. Some GRBs focus their energy into beams narrower than a laser pointer, slicing through space with surgical intensity. The real magic happens in the aftermath. As the jet slams into surrounding gas, it creates an afterglow, a lingering fingerprint of X-rays and radio waves that can last weeks. By dissecting these signals, scientists have uncovered something bizarre. The particles within seem to accelerate faster than shock wave models predict. It's as if the universe has a secret recipe for energy gain, one we've yet to crack. Some theories suggest magnetic turbulence supercharges the process, while others point to undiscovered quantum effects warping space-time itself. But here's the kicker. GRBs might be the missing link to those ultra-high-energy cosmic rays we've been chasing. A single burst could fling particles across billions of light years, seeding the cosmos with atomic projectiles moving faster than anything in our particle colliders. If proven, it would mean these fleeting explosions aren't just cosmic spectacles, they're the universe's ultimate power plants, forging particles at energies we can't begin to replicate. Yet for all their ferocity, GRBs leave us with a paradox. How can something so brief shape the cosmos so profoundly? The answer might lie not in the explosions themselves, but in the emptiness around them, the vast, near vacuum of cosmic voids where particles travel undisturbed for eons. And in these silent deserts, acceleration takes on a whole new meaning. Here's the next segment, crafted to flow naturally from the previous content while introducing fresh insights. It sounds like a cosmic paradox. The emptiest places in the universe might be hiding some of its most powerful particle accelerators. While we've been scouring black holes and supernova for answers, the real action could be unfolding in the vast, near-nothingness of cosmic voids. These sprawling deserts of space, stretching hundreds of millions of light-years across, aren't just empty. They're laboratories for a subtle, slow-motion acceleration process that challenges everything we thought we knew. Picture a lone proton drifting through one of these voids. There's no crushing gravity, no turbulent plasma, just an immense, silent expanse. But here's the twist: weak magnetic fields, faint as a whisper, still thread through these regions. Over millions of years, that proton can surf these fields like a cosmic escalator, steadily gaining speed without collisions to slow it down. By the time it reaches the edge of the void, it's packing staggering energy, all without the fireworks of a supernova or the violence of a black hole jet. Recent simulations reveal something even wilder. Voids might act like highways for ultra-high-energy particles, funneling them across the universe with eerie efficiency. Unlike dense environments where particles constantly crash and lose energy, these empty zones offer a free ride. It's the universe's version of a gravity assist, except instead of planets, the void itself becomes the slingshot. This flips the script on traditional acceleration theories. We've long assumed only violent, high-energy events could propel particles to extreme speeds. But voids suggest a quieter, more patient mechanism, one that works on scales so vast it's almost invisible to our telescopes, yet the evidence is mounting. When scientists map the paths of the highest energy cosmic rays, some trace back not to galaxies or clusters, but to these desolate stretches of space. Of course, there's a catch. If voids are cosmic particle highways, why don't we see even more ultra-high-energy rays? That's where the angle comes in, a mysterious bump in the cosmic ray spectrum that hints at an unseen balancing act between acceleration and loss. Somewhere in the void's embrace, particles might hit a natural speed limit, or perhaps the weak magnetic fields can only push them so far before another force takes over. Whatever the answer, one thing's clear: the universe doesn't need chaos to create extremes. Sometimes the greatest energies emerge from the quietest places, if only we know where to look. And speaking of quiet, there's another cosmic whisper hiding in plain sight: the faint but persistent hum of gravitational waves rippling through space-time itself. Could these invisible tremors also play a role in nature's grand acceleration scheme? Note, the transition to gravitational waves is a subtle handoff, keeping the narrative flowing toward the next topic without being abrupt. Picture a speedometer for the universe's fastest particles, only instead of numbers, it shows sudden bends in the data where physics seems to shift without warning. The cosmic ray spectrum's angle is one of these mysterious twists, a subtle kink appearing at around 1 quintillion electron volts. Far from random noise, this feature acts like a cosmic checkpoint, marking where the universe swaps one acceleration engine for something far more powerful. For decades, scientists believed supernova and neutron stars dominated the production of high-energy cosmic rays, but the angle challenges that assumption. Below this energy, particles likely originate within our Milky Way, hurled into space by stellar explosions. Above it, their extreme speeds point to forces beyond our galaxy's borders, possibly fueled by active galactic nuclei or colliding galaxy clusters billions of light-years away. The angle isn't just a data quirk, it's a frontier separating local physics from the universe's most violent distant engines. But here's where it gets even stranger. Some theories suggest the angle isn't just about where these particles come from, it's about how they survive the journey. At these energies, protons racing through space should collide with photons from the cosmic microwave background, losing energy like a marathon runner hitting a wall. Yet somehow they reach us intact. One explanation: the highest energy particles might be heavier atomic nuclei like iron, which plow through the cosmic fog more efficiently. Another possibility, unknown magnetic fields bend their paths, shielding them from catastrophic collisions. Crack this puzzle, and we'll do more than rewrite a textbook. We'll identify nature's ultimate particle accelerators, lurking in the depths of intergalactic space. And as we peel back the layers, another question emerges. If the ankle hints at distant powerhouses, what mechanisms inside them rev particles up to such impossible speeds? The answer might lie in a phenomenon so turbulent, it turns chaos into a precision tool: plasma instabilities. For all their destructive reputation, solar flares hide an extraordinary secret: they're cosmic particle accelerators in disguise. At the heart of these eruptions lies plasma, that seething fourth state of matter where atoms are ripped apart into a soup of charged particles. But plasma isn't just chaotic. Under the right conditions, it organizes itself with eerie precision, creating structures that funnel energy with jaw-dropping efficiency. Take the Weibel instability, a phenomenon where plasma, left to its own devices, spontaneously generates tangled magnetic fields. It works like this: when streams of charged particles flow unevenly, tiny fluctuations amplify into a web of magnetic threads. These threads act like a network of cosmic snares, trapping particles and whipping them to terrifying speeds. The result, a self-sustaining particle accelerator born from pure turbulence. What's revolutionary is how universal this process seems. The same instability sparks solar flares, shapes the jets of distant quasars, and even influences fusion reactors here on Earth. Laboratories are now recreating these extreme conditions, using lasers to trigger miniature versions of cosmic plasma storms. These experiments reveal something startling: nature's particle accelerators don't always need black holes or supernova. Sometimes all it takes is a spark of instability in the right environment. Yet the real marvel is how these discoveries blur the line between astrophysics and engineering. By decoding how plasma energizes particles in space, scientists are refining fusion technology, bringing us closer to harnessing star power here on Earth. It's a reminder that the universe's wildest phenomena often hold the keys to our own technological leaps. But plasma instabilities aren't the only architects of cosmic acceleration. Stretching across the universe like invisible highways, vast filaments of gas and dark matter weave galaxies together, and they might be silently orchestrating the most widespread particle acceleration of all. Stretching across the cosmos like invisible threads in a grand tapestry, the universe's largest structures aren't galaxies or clusters. They're the colossal filaments connecting them. These river-like webs of gas and dark matter, spanning hundreds of millions of light years, might seem too faint to matter, but hidden within their depths could lie one of nature's most widespread particle accelerators, humming silently between the stars. Here's how it works. As galaxy clusters, the universe's densest cities tug at each other through gravity. These filaments stretch and compress. That motion generates weak shock waves rippling through the sparse gas. While far gentler than a supernova's blast, these shocks have something critical: time. Over eons, they can steadily push particles to high energies, like a slow but relentless cosmic conveyor belt. Space telescopes have even detected a faint glow of gamma rays emanating from these regions, hinting at unseen particle collisions within the filament's depths. What makes this revelation groundbreaking is its sheer scale. Unlike the violent but localized bursts from black holes or dying stars, filament acceleration could be happening everywhere, a background hum of particle energization woven into the universe's very architecture. If confirmed, it means the voids we once thought empty might be interlaced with invisible highways, where particles gain speed across mind-boggling distances. Yet the filaments hold another clue: their alignment. Some studies suggest these structures might funnel and focus cosmic rays, explaining why certain high-energy particles arrive from seemingly blank patches of sky. It's as if the universe's scaffolding isn't just structure, it's an active participant in shaping how energy flows. While filaments work their quiet magic, there's a far louder player in the cosmic acceleration game, active galactic nuclei. These monstrous engines, powered by supermassive black holes, don't just brighten the night sky, they dominate it, flooding the cosmos with radiation that outshines entire galaxies. And their secrets might rewrite the rules of particle physics. At the center of nearly every massive galaxy, a ravenous beast lies in wait, not just consuming matter, but transforming it into some of the most intense radiation in existence. Active galactic nuclei, or AN, are the universe's ultimate power plants where supermassive black holes turn entire stars into cosmic fuel, spewing out jets so energetic they can outshine every star in their host galaxy combined. But these aren't just cosmic floodlights. AGN are particle accelerators on a staggering scale, hurling matter across millions of light years with precision that defies imagination. Their jets, structured like ultra-focused beams of plasma, aren't chaotic. They're sculpted by magnetic fields trillions of times stronger than Earth's, accelerating particles so efficiently that a single proton can reach energies millions of times greater than anything our most powerful colliders can produce. What's truly baffling is how these particles survive the journey. Theory suggests that at such extreme energies, protons should collide with photons from the cosmic microwave background, sapping their strength long before they reach us. Yet somehow they do, hinting that AGN jets might possess hidden mechanisms to shield their high-speed cargo, or that our understanding of particle physics is missing a critical piece. Even stranger are the so-called orphan gamma-ray flares, mysterious bursts of energy from AGN that appear without the usual accompanying light shows in other wavelengths. It's as if the universe is whispering its secrets in a code we've yet to crack. These flares might be clues to an even wilder acceleration process, perhaps involving hidden magnetic reconnection events or shock waves buried deep within the jets. The more we study these titans, the clearer it becomes. AGN aren't just outliers, they're central players in shaping how energy and matter flow through the cosmos. And if we can decode their mysteries, we might finally understand how the universe sustains such impossible extremes. But lurking behind the brilliance of active galaxies is an even deeper enigma, one that challenges the very limits of known physics. Some AGN emit particles with energies so high they shouldn't exist under current models. The answer may lie not in the jets themselves, but in the eerie quiet between them, an unseen interplay of forces we've only begun to glimpse. Here's your next segment, crafted to flow naturally from the previous content while diving into the mystery of orphan gamma-ray flares with fresh energy in the vast catalogue of cosmic oddities. Few puzzles are as stubborn as the case of the orphan flares, bursts of gamma rays that arrive without any fanfare, like fireworks in an empty sky. Unlike typical gamma-ray bursts linked to dying stars or black hole tantrums, these flares have no visible parent, no supernova, no merging neutron stars. Just raw, high-energy light blazing across the universe with no obvious source. It's as if the cosmos is teasing us with clues to a game we don't yet know the rules of. Theories scramble to explain these ghosts. Some suggest they're the work of dark accelerators, hidden objects like rogue black holes or neutron stars drifting unseen through interstellar space. Others propose something wilder, immense magnetic explosions in the depths of galaxy clusters, where plasma currents twist and snap without the drama of a visible explosion. The most intriguing idea, these flares might be echoes of particles colliding with dark matter, sparking brief but brilliant bursts that vanish before we can trace them home. What makes orphans so revolutionary isn't just their secrecy, it's how they expose gaps in our understanding of particle acceleration. Traditional models rely on violent, luminous events to explain high-energy radiation. Yet here's proof that the universe can whip particles to extreme speeds quietly, efficiently, and so far invisibly. Telescopes like the Fermi Gamma Ray Space Telescope are now hunting these phantoms, piecing together their paths like cosmic detectives. Every orphan flare caught is a potential key to rewriting the rulebook, but the implications stretch beyond mere curiosity. If dark accelerators exist, they could be everywhere, hidden architects shaping the energy landscape of the cosmos. And if dark matter's involved, we might finally have a way to map its shadowy presence through the trails of light it leaves behind. Yet for all their mystery, orphan flares hint at something even grander: the invisible threads tying cosmic rays to the evolution of galaxies themselves. Because when it comes to shaping the universe, sometimes the quietest forces leave the loudest echoes. Note, the transition to cosmic rays shaping galaxy evolution is subtly woven into the closing line, setting up the next topic without a jarring shift. Here's your next segment, seamlessly continuing the script while introducing the concept of cosmic rays as galaxy shapers with energy. While we've been tracking cosmic rays as high-speed travelers or collision byproducts, there's a twist. These particles aren't just passing through galaxies. They're actively shaping them. Like invisible sculptors, cosmic rays inject energy into the interstellar medium, heating gas, stirring magnetic fields, and even controlling where and when new stars ignite. This revelation flips the script. What if the universe's most energetic particles are also its most influential architects? Take star formation, a process we once thought was governed solely by gravity and cold gas. Recent simulations show cosmic rays crashing into molecular clouds like a cosmic defibrillator, jolting the gas with enough energy to prevent it from collapsing into stars. In some galaxies, this ray heating acts as a cosmic pause button, throttling star birth to a trickle. But in others, the effect reverses. By amplifying magnetic fields, cosmic rays can funnel gas into dense filaments, stellar nurseries where stars burst to life in spectacular chains. It's a delicate balancing act, one that explains why galaxies with similar gas reserves can look wildly different. The real masterpiece of this feedback loop. Galactic winds. When cosmic rays pour into a galaxy's outskirts, they heat the gas until it erupts outward, carrying away material that might have formed stars. Telescopes have spotted these winds laced with the chemical fingerprints of cosmic ray collisions streaming from galaxies like ours. Without them, galaxies might exhaust their fuel too quickly, burning out in a frenzied starburst. Instead, cosmic rays act as cosmic regulators, pacing a galaxy's evolution over billions of years. Yet for all their influence, cosmic rays guard one stubborn secret: their own origins. To decode how they shape galaxies, we first need to map where they come from, and that hunt has led scientists to an even stranger anomaly. Buried in the cosmic ray flux is an unexpected surplus of antimatter, specifically positrons. Their overabundance defies expectations, hinting at exotic sources we've yet to uncover. Here's your next segment, crafted to flow naturally from the previous content while diving into the Positron Excess mystery. Buried in the cosmic rays raining down on Earth lies a clue so strange, it's forced scientists to rethink the rules of particle physics. It's called the Positron Excess, an unexpected flood of antimatter particles that shouldn't exist in such numbers. Detectors like the Alpha Magnetic Spectrometer, mounted on the International Space Station, have spent years tallying these positrons, and the results are undeniable. There's far more of them than any conventional cosmic ray model predicts. It's as if the universe is hiding a secret factory for antimatter, and we're just starting to trace its blueprint: the leading suspects, pulsars and dark matter. Spinning neutron stars could be churning out positrons in their violent magnetic fields, flinging them into space like cosmic confetti. But there's a catch. The positron excess climbs steadily with energy, a trend that doesn't quite match pulsar emission patterns. That's where dark matter enters the scene. If these invisible particles occasionally annihilate each other, they'd produce positrons as a byproduct, a faint but detectable signature of the universe's most elusive substance. Yet the plot thickens. Some theorists argue we might be missing something even wilder: exotic acceleration mechanisms lurking in interstellar space. Picture rogue shock waves or magnetic vortices acting like antimatter forges, selectively boosting positrons to high energies. Others suggest quantum effects normally negligible on cosmic scales could be tweaking the rules in ways we've yet to imagine. Whatever the answer, one thing's clear: this isn't just about antimatter. It's a window into forces shaping the cosmos far beyond our current theories. And if quantum quirks are playing a role, the implications stretch even further. Tiny, subatomic behaviors might be scaling up to cosmic proportions, bending the laws of acceleration in ways Einstein never saw coming. That's where the real revolution could begin, not in the vastness of space, but in the ghostly dance of particles at the smallest scales imaginable. Note, the transition to quantum effects is woven organically into the closing line, setting up the next segment without a jarring shift. Here's your next segment, crafted to flow naturally while diving into quantum mechanics. Roll in cosmic acceleration with fresh energy. Zoom in far enough, past galaxies and stars, past atoms and even their tiny nuclei, until you're staring frothing, chaotic sea of spacetime itself. This is the quantum realm, where the rules of classical physics dissolve into uncertainty and particles blink in and out of existence in a heartbeat. It might seem too small to matter in the vastness of cosmic acceleration, but new theories suggest the quantum world could be pulling invisible strings, shaping how particles reach unfathomable speeds. Take quantum turbulence, a phenomenon where spacetime itself churns like a stormy ocean at microscopic scales. In extreme environments like the magnetosphere of a neutron star or the shock front of a supernova, this turbulence might amplify magnetic fields in fleeting, intense bursts. Think of it as a quantum-scale whirlpool, trapping particles and flinging them forward with unprecedented efficiency. Laboratory experiments using ultra-powerful lasers are now recreating these conditions, and early results hint at something extraordinary. Quantum effects could be acting as miniature particle boosters, hidden within larger cosmic accelerators. Then there's the vacuum itself. Far from being empty, it's a seething foam of virtual particles that pop into existence for fractions of a second. Under the intense gravitational grip of a black hole or neutron star, these fleeting particles might get stretched by tidal forces, converting their borrowed energy into real particles with measurable momentum. It's as if the universe has a secret ledger, balancing the books of energy on scales we're only beginning to detect. Of course, these ideas toe the line between physics and speculation, but that's what makes them thrilling. If quantum effects do play a role, it would mean nature's acceleration mechanisms are even more intricate than we imagined, woven into the fabric of reality at every scale. And as experiments push closer to validation, we're forced to confront a tantalizing question. Could the key to cosmic rays lie not in the grand violence of black holes, but in the whispers of the quantum void? Speaking of cosmic ray mysteries, there's another puzzle looming over the field, one that's haunted physicists for decades. It's called the GZK Cut-Off, and it might just reveal where the universe draws its ultimate speed limit. Note, the transition to the GZK Cut-Off is smoothly embedded in the closing line, maintaining narrative momentum. Here's your next segment, crafted to flow naturally from the previous content while diving into the GZK paradox with fresh energy. Imagine the universe enforcing a cosmic speed limit, one so strict that even the most energetic particles can't break it without consequences. That's the essence of the Grison's Cut-Off, or GZK limit, a theoretical barrier calculated decades ago that should prevent ultra-high energy cosmic rays from traveling vast distances. According to the rules, any particle blasting through space with energy beyond 50 quintillion electron volts should collide with photons from the cosmic microwave background, the afterglow of the Big Bang. These crashes would drain their energy long before reaching Earth, like a marathon runner hitting wall after wall. But here's the catch: we've detected particles that shouldn't be here. Multiple observatories, from the Pierre Auger Array to the Telescope Project, have spotted cosmic rays screaming past the GZK threshold with no sign of slowing down. It's as if these particles bypassed the universe's toll booths entirely. This contradiction has split physicists into two camps: those scrambling to find flaws in our detectors and those ready to rewrite the textbooks. Could measurement errors be to blame? Or is this the first hint of something far stranger physics beyond our current models? One radical theory suggests these rogue particles might be exotic relics from the early universe, like cosmic defects, leftover wrinkles in spacetime from the Big Bang's violent infancy. Another idea points to Lorentz invariance violation, a scenario where the very rules of relativity bend slightly at extreme energies, letting particles cheat the GZK limit. Then there's the dark horse candidate, magnetic monsters. If intergalactic magnetic fields are stronger than we thought, they could bend particle paths, masking their true origins and making them appear to defy the GZK rule. Yet the most tantalizing possibility is that these outliers aren't cosmic rays at all, but their stealthy siblings, neutrinos. Unlike charged particles, neutrinos barely interact with matter or light, slipping through the cosmic microwave background unimpeded. If some ultra-high-energy events produce neutrino-dominated jets, we might be glimpsing their secondary signals without realizing it. That brings us to the next frontier in this puzzle: neutrinos as cosmic messengers, and the accelerators capable of launching them. Note, the transition to neutrinos is subtly woven into the closing line, maintaining narrative flow without repetition. Here's your next segment, crafted to flow naturally from the previous discussion of ultra-high energy cosmic rays, while introducing neutrinos with fresh energy and depth. While cosmic rays leave trails of charged particles, there's another messenger slicing through universe, one so elusive it barely notices galaxies, stars, or even planets in its path. Neutrinos, the universe's ghost particles, pass through matter like shadows through walls, carrying secrets from the most violent cosmic engines without a whisper of distortion. Unlike their flashy gamma-ray cousins, these phantoms don't announce their arrival with bursts of light. Instead, they slip past detectors silently until they don't. Deep beneath the Antarctic ice, the Ice Cube Observatory has turned this stealth into an advantage. By monitoring tiny flashes of blue light, created when a neutrino rarely collides with an atom, scientists have caught high-energy neutrinos that could only originate from cosmic accelerators like active galactic nuclei or gamma-ray bursts. What makes these detections groundbreaking isn't just their energy, it's their path. Unlike charged cosmic rays, which magnetic fields bend and scramble, neutrinos travel in near-perfect straight lines, pointing like cosmic arrows back to their sources. But the real magic lies in what they reveal about acceleration itself. When a neutrino arrives with energies topping 1 quadrillion electron volts, it implies its birthplace, whether a supermassive black hole's jet or a collapsing star, operates with freakish efficiency. IceCube's data suggests some neutrinos might even be byproducts of proton-proton collisions within these accelerators, offering a direct window into processes hidden behind veils of dust and plasma. It's like decoding a murder mystery where the neutrinos are the fingerprints invisible to the naked eye but unmistakable under scrutiny. Yet for all their promise, neutrinos guard one frustrating trait: their aloofness. Detecting enough of them to map the cosmos requires instruments of staggering scale like ice cubes, cubic kilometer of sensor-laden ice, and even then, most slip through unnoticed. But when they do interact, they deliver something no other particle can: pure, unaltered intel from the universe's most forbidden frontiers. As we piece together these ghostly clues, another theoretical player lurks in the shadows, one that could rewrite the rules of magnetism itself. If neutrinos are the universe's silent witnesses, magnetic monopoles might be its most revolutionary architects. Note, the transition to magnetic monopoles is subtly woven into the closing line, maintaining momentum while hinting at the next topic without repetition. 20th insight: magnetic monopoles and exotic acceleration. The universe loves symmetry, equal parts matter and antimatter. Positive and negative charges, but magnetism has always been the exception. Every magnet we've ever found, from fridge stickers to neutron stars, comes with two poles, a north and a south. What if that wasn't always the case? Enter magnetic monopoles, hypothetical particles carrying just a single magnetic charge, like an electron but for magnetism instead of electricity. They've never been detected, yet theories from quantum physics to grand unification insist they should exist. And if they do, they might hold the key to acceleration mechanisms wilder than anything we've dreamed of. Picture a monopole drifting through interstellar space. Unlike ordinary particles, its magnetic charge wouldn't just interact with fields, it could reshape them, twisting the fabric of spacetime itself into particle-accelerating highways. Some models suggest monopoles could act like cosmic catalysts, triggering chain reactions that convert ordinary matter into ultra-high-energy cosmic rays. Others propose they're relics from the early universe, frozen into existence during the Big Bang's cooling, lurking in the voids or even trapped inside stars. The hunt for these phantoms has taken scientists from deep underground labs to particle colliders. Experiments like Mo et al. At CERN scour collisions for telltale tracks. Monopoles would leave ionizing trails unlike anything else. Meanwhile, cosmic ray detectors listen for their faint signatures in high-energy events. So far, silence, but absence of evidence isn't evidence of absence, especially when the payoff could rewrite physics. Proving monopoles exist wouldn't just explain cosmic rays. It might reveal hidden layers of reality, where forces unify in ways we've only glimpsed in equations. And yet, for all their theoretical allure, monopoles force us to confront a humbling truth. The universe's rulebook might still have chapters we haven't opened. Which brings us to a very real and very massive mystery closer to home. Stretching above and below our galaxy's core, two gargantuan orbs of gamma rays glow with energies that defy easy explanation. They're called the Fermi Bubbles, and their secrets could rewrite the story of the Milky Way's most violent past. Note, the transition to Fermi Bubbles is subtly woven into the closing lines, maintaining momentum while introducing the next topic organically. 21st insight: Fermi Bubbles and galactic acceleration rising from the heart of the Milky Way like twin titans, two colossal orbs of gamma rays stretch tens of thousands of light years into space, one above the galactic plane, one below. These are the Fermi Bubbles, and they're not just remnants of some ancient cataclysm. They're a living record of our galaxy's explosive past. Discovered just over a decade ago by NASA, a Fermi Gamma Ray Space Telescope, these faint but massive structures glow with energies that hint at a violent event, one likely fueled by our own supermassive black hole, Sagittarius A, in a long-forgotten feeding frenzy. But what keeps these bubbles shining long after their creation? The answer lies in their intricate physics. Inside these vast structures, particles whip through turbulent magnetic fields, accelerated by shocks rippling outward from the galactic center. Some theories suggest these shocks act like cosmic superspreaders, continuously energizing particles rather than just preserving ancient ones. Others point to magnetic reconnection events, those same explosive rewirings seen in solar flares, unfolding on a galactic scale, injecting fresh energy into the bubble's faint glow. What's truly astonishing is the scale of influence these bubbles wield. They're not passive fossils, they're dynamic structures actively shaping our galactic environment. As high-energy particles leak from their edges, they mix with the Milky Way's halo gas, potentially regulating star formation in the outer reaches of the galaxy. It's a stark reminder that even a quiet black hole like Sagittarius leaves an enduring legacy, one written in gamma rays and charged particles. Yet for all their grandeur, the Fermi Bubbles raise a pressing question. If our galaxy's central engine can sculpt structures this vast, what does that mean for more active galaxies? The answer might lie in the universe's most energetic particles, the ones that seem to arrive from everywhere and nowhere at once. Note, the transition to isotropy is subtly embedded, avoiding repetition while naturally leading into the next segment. 22nd Insight, the cosmic ray riddle. Why every direction looks the same picture standing in the middle of a battlefield. Whizzing past, but instead of coming from the enemy's position, they're striking from every direction at once. That's the essence of the cosmic ray isotropy puzzle. These ultra-high-energy particles don't point back to obvious sources like black holes or exploding stars. Instead, they rain down evenly across the sky, as if the universe itself is playing a game of cosmic darts with perfect, frustrating randomness. For scientists, this uniformity is a double-edged clue. On one hand, it could mean there are countless weak accelerators scattered throughout space, each contributing a trickle of particles, collectively flooding us from all angles. Think of it like 1,000 faint light bulbs lighting up a room. No single source dominates, but together they illuminate everything equally. On the other hand, there's a wilder possibility something we can't yet see is scrambling the paths of cosmic rays, twisting their trajectories so thoroughly that their origins are erased. Magnetic fields are the prime suspect. If intergalactic space is threaded with stronger or more tangled magnetism than we've measured, it could act like a cosmic blender, churning particle paths beyond recognition. Simulations show that even weak fields stretched across millions of light years could redirect particles so dramatically that their arrival directions tell us nothing about where they began. It's a humbling thought. The universe might be hiding its most powerful accelerators behind an impenetrable veil of magnetism. Yet there's a third, even more intriguing option. What if the isotropy isn't a smokescreen but a spotlight? Some theorists argue that the most extreme cosmic rays, those with energies beyond the GZK limit, might come from outside our local cosmic neighborhood. If true, their uniform spread could reflect the vast-scale structure of the universe itself, with filaments and voids funneling particles toward us from all directions. No matter the answer, one thing's certain: cracking the isotropy puzzle won't just reveal where cosmic rays come from, it'll expose hidden forces shaping the cosmos in ways we've barely begun to map. And as we untangle this riddle, another mystery emerges, one that hits closer to home. These same particles, capable of warping galaxies, might also have played an unlikely role in sparking life itself. Note, the transition to cosmic rays' role in life's origins is woven into the closing line, avoiding repetition while maintaining momentum. 23rd Insight, cosmic rays and the spark of life long before the first cells stirred in Earth's ancient oceans. A hidden force might have set the stage for life itself. Cosmic rays, those same high-speed particles born in supernova and black hole jets, could have been cosmic chemists, weaving the building blocks of biology from raw interstellar ingredients. It's a staggering idea. The universe's most violent accelerators may have quietly nudged existence into being. Here's how it could work. Picture a frigid molecular cloud drifting through space, packed with simple gases like hydrogen, carbon monoxide, and ammonia. Normally, these molecules would drift forever, too cold and inert to react. But when a cosmic ray tears through, it ionizes atoms, knocking electrons loose and leaving behind charged fragments hungry to bond. Suddenly, that dormant cloud becomes a cosmic laboratory, forging complex organic molecules like formaldehyde or even amino acids, the precursors to proteins. Experiments on Earth have recreated these conditions, showing how ionizing radiation can stitch simple gases into life's molecular alphabet, but the plot thickens beyond chemistry. Cosmic rays might also have shaped life's cradle in a subtler way by influencing Earth's early climate. Some studies suggest these particles could have seeded cloud formation in the primordial atmosphere, scattering sunlight and regulating temperatures during the planet's most vulnerable epochs. It's a fragile thread connecting particle physics to habitability, one that hints at how deeply the cosmos is woven into our origin story. Of course, this isn't proven science yet. The leap from ionized gases to living cells remains vast, and cosmic rays are just one piece of a sprawling puzzle. But their potential role reminds us that the universe doesn't just accelerate particles, it might accelerate possibility. And if these rays helped forge life here, could they be doing the same right now in some distant gas cloud? The answer, like so much in this cosmic mystery, is written in the particles still raining down upon us. Speaking of unanswered questions, there's another enigma lurking in the cosmic ray spectrum, one so perplexing it's earned its own name. Astronomers call it the Pevatron, and its existence could rewrite what we know about nature's ultimate accelerators. 24th Insight, hunting for Pevatrons, nature's ultimate accelerators deep in the cosmos. Something is hurling particles with energies so extreme, they make the Large Hadron Collider look like a toy. These are Pevatron's elusive cosmic accelerators capable of launching particles to petaelectronvolt energies, a scale where the rules of physics strain under the sheer force. That's 1,000,000 times more powerful than the protons circling inside CERN colliders. But here's the catch. While we've detected these ultra-high-energy cosmic rays for decades, their birthplaces remain one of astrophysics' greatest unsolved mysteries. The hunt has zeroed in on supernova remnants, the chaotic debris fields left behind by exploding stars. These turbulent graveyards should, in theory, act as natural particle colliders, with shock waves slamming protons and atomic nuclei to PV energies. Yet when scientists point telescopes at candidates like the Cygnus cocoon or RxJ 1713, the evidence stays frustratingly murky. Some show tantalizing gamma-ray signals hinting at PV acceleration, but none deliver the smoking gun. It's like tracking a ghost by its shadow. We see the aftermath, but the engine itself stays hidden. Part of the challenge lies in cosmic rays' maddening ambiguity. Unlike light, which travels straight to our telescopes, charged particles zigzag through interstellar magnetic fields, erasing clues about their origins. That's why detectors like Tibet ASGAMA and Hawk in Mexico don't just look for cosmic rays, they search for gamma rays and neutrinos, secondary signals created when PV particles collide with gas or starlight. These messengers can't be deflected, offering a clean path back to their sources. But the real breakthrough might come from multi-messenger astronomy, combining data from gamma rays, neutrinos, and even gravitational waves. If a supernova remnant lights up in gamma rays and emits a flood of high-energy neutrinos, it could finally confirm a Pevatron at work. The pieces are falling into place. We're on the verge of catching nature's mightiest accelerators in the act. Yet for all their power, Pevatrons aren't just cosmic oddities. Their influence stretches far beyond their birth sites, shaping the very environment of our solar system. Because when these particles flood the galaxy, they don't just vanish, they weave into the invisible tapestry of space weather, stirring storms that can ripple from the edges of the Milky Way all the way to Earth. 25th Insight, Cosmic Rays and the Invisible Storm. Every second, our planet is bombarded by an invisible hailstorm, not of rain or ice, but of particles traveling near light speed. These cosmic rays, born in the fury of supernova and black holes, don't just light up the night sky with auroras. They crackle through satellites, disrupt electronics, and even penetrate the bodies of astronauts, posing risks that stretch far beyond Earth's atmosphere. This isn't just theoretical, it's space weather, a silent tempest shaping the future of exploration and technology. Take the International Space Station, orbiting high above Earth's protective magnetic shield. Astronauts there report flashes of light behind closed eyelids, not hallucinations, but cosmic rays zipping through their retinas. Over months, this exposure can damage DNA, raising the stakes for missions to Mars or beyond. Meanwhile, down on Earth, airlines monitor radiation levels at cruising altitudes, where cosmic rays occasionally fry delicate avionics or even flip bits in computer memory, causing glitches with no obvious cause. But here's the game changer. By decoding how cosmic accelerators work, scientists are learning to predict these particle storms. Just as meteorologists track hurricanes, space weather models now map the ebb and flow of high-energy particles, using clues from solar flares, supernova remnants, and even distant quasars. Satellites like NOAA R-series act as early warning sentinels, giving astronauts and grid operators precious hours to take cover or power down sensitive systems. This isn't just about survival, it's about unlocking the solar system. Better forecasts mean safer routes for crewed missions, more resilient satellites, and even new materials to shield future moon bases. The physics of cosmic acceleration, once a curiosity, is now a lifeline. And as we peer deeper into the particle deluge, another enigma surfaces, one written in the universe's rarest ink. Hidden within the cosmic ray flood lies a strange excess of antimatter, a ghostly fingerprint pointing to mysteries we've only begun to unravel. 26th Insight, the antimatter enigma. When the universe breaks its own rules, something strange is raining down from space. Not just ordinary particles, but their mirror opposites, antimatter. While positrons get most of the attention, cosmic rays carry another surprise. An unexpected surplus of antiprotons, the antimatter counterparts to regular protons. These shouldn't be here in such numbers. Conventional physics suggests they'd mostly annihilate long before reaching us, colliding with matter in interstellar space and vanishing in bursts of energy. Yet detectors keep tallying them up, leaving scientists with a cosmic accounting error they can't ignore. Some of these rogue antiprotons likely come from spallation, high-energy cosmic rays smashing into interstellar gas and splitting atoms apart, like a wrecking ball shattering a wall into odd fragments. But the math doesn't quite add up. The observed excess hints at something beyond mundane collisions, something exotic, maybe even something dark. If dark matter particles occasionally annihilate each other, as some theories suggest, they could flood the galaxy with antimatter as a byproduct. Experiments like MS-02 aboard the International Space Station are sifting through the cosmic ray influx, hunting for patterns that might betray dark matter's fingerprints. Yet there's another twist. Antimatter's journey isn't just about origins. These particles weave through magnetic fields differently than their matter twins, potentially sculpting their own invisible highways across the galaxy. If we can map their paths, we might uncover hidden structures, cosmic shortcuts, or traps where antimatter piles up in unexpected ways. It's a reminder that the universe's ledger isn't balanced. It's lopsided in ways we're only starting to measure. But if antimatter's surplus stretches our understanding of particle physics, the next revelation bends reality itself. What if cosmic accelerators aren't just natural phenomena, but echoes of other universes? The multiverse theory might hold clues to the most extreme particle energies we've ever detected. Note, transition to multiverse theory is subtly embedded, avoiding repetition while signaling a conceptual leap. 27th insight, cosmic accelerators and the multiverse when physics borrows from elsewhere. The most radical explanation for ultra-high-energy cosmic rays isn't just in our universe, it might stem from beyond it. Multiverse theories, once the stuff of speculative physics, are now creeping into discussions about nature's most powerful particle accelerators. The reasoning: some cosmic rays arrive with energies so extreme, they defy what our universe's known laws should allow. Could these outliers be cosmic hitchhikers slipping through from neighboring dimensions? It's not as far-fetched as it sounds. In certain string theory models, universes with different physical constants could exist alongside ours, separated by membranes or higher dimensional folds. Under rare conditions, these membranes might leak, transferring energy across boundaries. If a high-energy event, say, a black hole collision, occurred in a universe where the speed of light is higher, the resulting particles could carry that exotic energy into our cosmos, appearing as inexplicable cosmic rays. Even wilder are proposals like false vacuum decay, the idea that our universe isn't in the lowest possible energy state. If a bubble of true vacuum formed in another universe and expanded into ours, the collision could unleash energies dwarfing anything naturally occurring here. The cosmic rays we've dubbed "oh my god" particles, those with energies exceeding 100 quintillion electron volts, might be the shock waves from such an event. Of course, this is speculative territory. Critics argue that multiverse explanations risk becoming a catch-all for unsolved puzzles. Yet the fact that these ideas are even on the table underscores how baffling cosmic acceleration remains at its extremes. Whether the answer lies in other dimensions or undiscovered physics closer to home, one truth is clear: the universe's particle accelerators still have secrets we've barely begun to uncover. And those secrets might not stay hidden forever. A new generation of observatories equipped with AI-driven analysis and unprecedented sensitivity is about to turn the cosmos into an open book. The next chapter in this story could rewrite physics itself. Note, transition to future observatories is woven organically, avoiding repetition while propelling momentum. 27th insight, cosmic accelerators and the multiverse. What if the universe's most powerful particle accelerators aren't ours at all? Beyond the violent spectacle of black holes and supernova, an even wilder possibility lurks: these extreme energies might be whispers from other universes. It's a concept ripped from the edges of theoretical physics, where cosmic collisions between dimensions could leave behind scars in the form of inexplicable particle surges. The idea hinges on a radical premise: our universe might not be alone. In certain string theory models, higher dimensional brains, think of them as floating cosmic membranes, could occasionally brush against one another, releasing unimaginable energy. If such an event happened eons ago, the shock waves might still ripple through space today, creating pockets where particles accelerate to impossible speeds without any visible source. Some physicists even speculate that infamous ultra-high-energy cosmic rays, like the so-called "oh my god" particles, could be debris from these ancient collisions, trespassers from a reality with entirely different physical laws. Of course, this remains speculative. Critics argue that multiverse theories risk explaining too much by explaining nothing, a cosmic just-so story. Yet the fact that these ideas are taken seriously in peer-reviewed journals underscores how desperate we are to solve the puzzle. When nature defies every known acceleration mechanism, scientists must stretch their imaginations to the breaking point. But if crossing dimensions seems like science fiction, the next paradox is even stranger: a phenomenon where particles appear to break causality itself. Because lurking in the math of cosmic acceleration is a ghostly suggestion. What if some high-energy events aren't just bending the rules of space but time? Note the transition to time reversal is subtly woven in, maintaining momentum while avoiding repetition. 28th insight. When time runs backward, cosmic acceleration's strangest symmetry in the heart of a plasma storm or the wake of a supernova. The universe occasionally plays a trick on physics. It runs the film backward. Certain particle acceleration processes don't just defy gravity or magnetism. They defy time itself. At least that's how it appears. Scientists call this time reversal symmetry, a phenomenon where the steps of acceleration look identical whether you observe them moving forward or in reverse. It's as if nature scribbled the same equation in both directions, leaving physicists to wonder, does cause and effect still apply at cosmic extremes? Take magnetic reconnection, that explosive rewiring of field lines we've seen in solar flares and black hole jets. Advanced plasma simulations reveal something bizarre. When you reverse the simulation's clock, the energy release and particle acceleration often mirror the original process. Unlike everyday events, where a shattered glass never reassembles itself, these cosmic processes seem indifferent to time's arrow. Some theories suggest this symmetry hints at deeper, hidden laws governing how energy transfers at quantum scales, where particles might temporarily forget which way time flows. But here's where it gets even stranger. If acceleration can be time-symmetric, could certain cosmic rays carry echoes of future events? Before you dismiss that as sci-fi, consider this. Quantum mechanics already allows for microscopic time reversal in particle interactions. While we're not claiming cosmic rays are literal messages from tomorrow, their behavior might encode clues about physics operating outside our linear experience of cause and effect. This paradox isn't just philosophical, it's practical. Unraveling time symmetry could explain why some high-energy particles arrive with properties that defy traditional acceleration models. Maybe the universe's rulebook has pages we've yet to read, where time folds back on itself in ways Einstein never anticipated. And if that's true, the next frontier might not just span space, it could twist through dimensions we've never seen. Because when time bends, space might ripple, and lurking in those ripples could be the most elusive prediction of all, proof that our universe isn't alone. The hunt for cosmic rays' dimensional footprints is already underway, and what we find might rewrite reality as we know it. 29th insight. The hidden dimensions of cosmic rays. What if the universe's highest energy particles aren't just punching through space, but slipping between dimensions? For decades, cosmic rays have baffled scientists with energies that seem to defy known physics. But one radical explanation suggests these particles might be brushing against realities beyond our own. String theory, the ambitious framework aiming to unify all forces of nature, proposes that our universe could harbor extra-spatial dimensions, tiny, curled-up realms far smaller than an atom, yet profoundly shaping the fabric of reality. Here's the tantalizing twist. If these hidden dimensions exist, ultra-high-energy cosmic rays might occasionally leak into them like ripples passing through a folded sheet. This interaction could leave behind subtle fingerprints, unexplained gaps in energy signatures, or particles that appear to lose momentum without colliding with anything in our three-dimensional world. Detectors like the Pierre Auger Observatory are now scouring cosmic ray data for these anomalies, hunting for statistical bumps or dips that hint at something beyond ordinary spacetime. Of course, extra dimensions remain theoretical. No experiment has confirmed their existence, but the search is more than wishful thinking. If cosmic rays do interact with them, it could explain why some particles arrive with energies that seemingly break the universe's speed limits. The math suggests particles might even split across dimensions, shedding energy in ways that look like violations of known physics from our limited perspective. Yet for all their mystery, these dimensions aren't just abstract math. They could be the key to unlocking gravity's secrets, why it's so weak compared to other forces, or even revealing the true structure of space-time itself. Every ultra-high-energy cosmic ray that streaks through our detectors might carry more than just raw power. It could be a message from realms we've yet to perceive. And as we push the boundaries of detection, another puzzle looms, one that tests the very limits of what particles can tell us. How far can cosmic rays travel before the universe itself erases their origins? The answer might lie in a concept called the cosmic ray horizon, and it's about to redefine our search for the universe's most powerful engines. 30th Insight, the cosmic ray horizon, where the universe draws the line. Every signal in the cosmos faces a fundamental limit, not just from distance, but from the very fabric of space itself. Light has its horizon, the observable edge of the universe, but cosmic rays face their own invisible barrier, a threshold where the expanding cosmos and its sea of background photons conspire to drain their energy, erasing their origins like footprints in a cosmic tide. This isn't just a theoretical curiosity, it's a frontier that could redefine how we map the universe's most violent engines. Picture a proton racing across billions of light years. Along the way, it smashes into photons left over from the Big Bang, the cosmic microwave background. These collisions chip away at its energy, slowing it down until its original source becomes untraceable. The higher the particle's initial energy, the sooner it hits this wall. For ultra-high-energy cosmic rays, the horizon might be as close as a few 100 million light-years, meaning anything beyond that distance is effectively invisible to our detectors. It's like listening to a radio station that fades to static. No matter how loud the signal starts, the universe eventually muffles it. But here's what makes this limit revolutionary. It's not just a dead end. By studying where cosmic rays stop arriving, scientists can reverse engineer the distribution of their sources. If we detect a sudden drop-off in particles above a certain energy, it could signal the presence of a distant accelerator just beyond the horizon's edge. Telescopes like the Pierre Auger Observatory are already using this principle to sketch a crude map of cosmic powerhouses, hinting at clusters of activity in otherwise blank patches of sky. The implications stretch even further. If the cosmic ray horizon aligns with gaps in our observations, it might explain why some ultra-high-energy particles seem to appear out of nowhere. Their birthplaces could lie just beyond the edge of our perceptual reach, hiding in the universe's blind spots. Yet for every mystery solved, another emerges. How do we peer past these limits? That's where a game-changing tool enters the fray, one that's not bound by the laws of physics but thrives on them. Artificial intelligence is turning cosmic ray research into a high-stakes treasure hunt, and the discoveries are just beginning. Transitions subtly woven into the closing line, pivoting to AI's role without repetition. 31st Insight, AI and the future of cosmic acceleration studies a quiet revolution is unfolding in astrophysics, not in distant galaxies or particle colliders, but in lines of code. Machine learning has become astronomy's most tireless assistant, scanning petabytes of cosmic ray and gamma ray data with superhuman precision. Where human researchers might spend years sifting through noise, AI detects subtle patterns in seconds, flagging anomalies that could rewrite our understanding of particle acceleration. Take the Fermi Gamma Ray Space Telescope's decade-long dataset, a treasure trove of high-energy events. Traditionally, identifying candidate accelerators meant painstaking manual analysis, like finding needles in a cosmic haystack. Now, neural networks trained on known sources comb through the noise, spotting faint signals that slipped past earlier searches. Some of these discoveries aren't just new, they're unexpected. AI has unearthed gamma-ray flares from seemingly quiet galaxies and pinpointed supernova remnants with bizarre energy signatures, hinting at acceleration mechanisms we've never modeled. What makes this shift groundbreaking isn't just speed, it's the ability to ask questions we didn't know to ask. Clustering algorithms have grouped cosmic rays by energy and trajectory, revealing hidden subcategories that might trace back to different astrophysical engines. Other models simulate magnetic field interactions in ways that brute force calculations can't, suggesting how particles might surf turbulence in galactic filaments or black hole jets. The result, a living map of the cosmos's particle highways updated in near real time. Yet for all its power, AI has its limits. These tools don't interpret, they correlate. A neural network might flag a strange gamma-ray burst, but it takes human intuition to ask whether it's a pulsar's hiccup or dark matter's fingerprints. The future lies in partnership, machines narrowing the search, scientists probing the meaning. As we harness this synergy, another challenge looms, one that even AI can't sidestep. Despite our advances, there's a glaring mismatch between the energy cosmic rays should lose during their journeys and what we actually detect. Dubbed the energy crisis in cosmic ray physics, this paradox might force us to rethink everything from intergalactic magnetism to the nature of spacetime itself. Note smooth transition to the next topic without repetitive phrasing. 30-second insight, the cosmic ray energy crisis when the universe breaks its own rules. Picture pouring a cup of water into a sieve, only to watch it come out the other side completely dry. That's essentially the puzzle physicists face with ultra-high-energy cosmic rays. According to our best models, these particles should lose most of their energy as they travel across the universe, yet somehow they arrive at Earth packing unimaginable punch. This glaring mismatch between prediction and observation isn't just a quirk, it's a full-blown crisis in cosmic ray theory, forcing scientists to question whether we're missing something fundamental about how the universe accelerates matter. The heart of the problem lies in the cosmic microwave background, the faint afterglow of the Big Bang. Space isn't empty, it's filled with these relic photons, and when a high-energy proton smashes into one, it loses momentum like a race car hitting a wall. Calculations show that for particles over 50 quintillion electron volts, the so-called GZK limit, intergalactic space should act like cosmic quicksand, sapping their energy long before they reach us. Yet detectors keep catching them anyway, with no obvious source nearby to explain their endurance. This paradox has split researchers into two camps. Some argue we've underestimated the power of known accelerators, that supermassive black holes or colliding galaxy clusters might harbor hidden mechanisms to boost particles even beyond current theories. Others suspect the answer lies deeper, in physics beyond the standard model. Could cosmic rays be hinting at exotic particles, unknown forces, or even flaws in our understanding of spacetime itself? The stakes couldn't be higher. Solving this crisis might require rewriting the rulebook for how energy moves through the cosmos. Yet for all the uncertainty, these unruly particles offer an unexpected gift. Their stubborn refusal to fade could be the key to glimpsing the universe's infancy. Because if cosmic rays can traverse billions of light years without losing steam, they might carry pristine fingerprints of the early cosmos, a time when the first galaxies flickered to life, and the laws of physics may have operated in ways we can't yet imagine. And that's where the story takes a breathtaking turn. These high-energy messengers could be more than cosmic anomalies. They might be time capsules, preserving secrets from an era before stars even existed. To decode them, we'll need to venture back to the dawn of everything, when the universe was a seething cauldron of raw potential. The answers we're chasing today might have been written 13 billion years ago in the fiery aftermath of creation itself. 33rd insight, time capsules from the dawn of time. Forget ancient fossils or ice cores. The universe's most revealing relics might be raining down on us right now, invisible to the naked eye. Ultra-high-energy cosmic rays aren't just astrophysical oddities. They could be celestial time machines carrying whispers from the universe's infancy. If these particles have journeyed uninterrupted for billions of years, some perhaps dating back to the Big Bang itself, their very existence might hold clues about how space-time, matter, and energy behaved when everything was new. Think of it like finding a perfectly preserved letter from the first day of creation. Cosmic rays born in the chaos of the early universe would have encoded information in their energy, composition, and trajectory details that could reveal the temperature of primordial plasma, the strength of infant magnetic fields, or even the seeds of the first galaxies. The challenge: isolating these ancient particles from the modern cosmic noise. It's like trying to hear a single voice in a stadium full of screams. Detectors are already hunting for these rarities. When an ultra-high-energy cosmic ray slams into Earth's atmosphere, it triggers a cascade of secondary particles, a faint echo of its origins. By analyzing these showers, scientists can work backward, reconstructing the original particle's energy and direction. Some theories suggest that if certain outliers in the data defy all known acceleration models, they might be relics of cosmic inflation, the universe's explosive growth spurt in its first trillionth of a second. Yet the real breakthrough lies ahead. Next-generation observatories like the proposed Particle Astrophysics Magnetospheric Observatory aim to catch these particles before they hit the atmosphere, minimizing distortion. It's the difference between studying a fresco through a fogged window and seeing it up close, brushstroke by brushstroke. If successful, we might finally read the universe's first chapter, written not in ink but in particles hurled across time. But as we push toward these primordial frontiers, another enigma emerges. Why do cosmic rays seem to hit an invisible ceiling? The universe appears to enforce its own speed limit, and the reason could rewrite our understanding of space itself. Note the transition to the acceleration threshold is subtly embedded, avoiding repetition while propelling the narrative forward. 34th insight: the universe's hidden speed bump. Why some particles don't make the cut. Imagine a cosmic bouncer standing at the door of the universe's most exclusive particle accelerators, black holes, pulsars, and active galaxies letting only highest energy particles past the velvet rope. This isn't science fiction, it's the acceleration threshold phenomenon, a curious rule that seems to govern some of the cosmos's most powerful engines. Unlike supernova, which fling particles across the energy spectrum, certain objects like pulsars and active galactic nuclei act like precision filters, ejecting only particles that meet a minimum energy requirement. It's as if nature has set a secret speed limit, and cracking the code could reveal a universal blueprint hidden in the chaos. Take pulsars, those spinning neutron stars we've seen powering nebulae like the Crab. Their magnetic fields aren't just strong, they're finely tuned, acting like particle sieves. Below a certain energy, charged particles get trapped in the star's magnetosphere, spiraling harmlessly along magnetic field lines. But cross that threshold and suddenly they're rocketed into space at nearly light speed. The same selectivity shows up in active galactic nuclei, where jets seem to ignore low-energy particles, focusing instead on accelerating only the most energetic candidates. This isn't random, it suggests an underlying physics recipe, one that might link these wildly different objects under a single cosmic law. What's truly fascinating is what this means for unification. If distinct accelerators, from tiny pulsars to galaxy-spanning jets, share the same energy threshold rules, it could hint at a universal mechanism governing particle ejection. Some theorists point to plasma instabilities or resonant wave interactions, processes that naturally amplify only certain energy ranges. Others wonder if spacetime itself plays a role, with extreme gravity or magnetism acting like a coarse filter. But here's the real twist. If thresholds exist, they might leave traces in an entirely unexpected messenger: gravitational waves. The same violent processes that sort particles by energy could ripple spacetime itself, offering a backdoor to mapping cosmic accelerators even when light fails. And that's where the next frontier begins, listening for the universe's quietest tremors to decode its loudest explosions. Note, transition to gravitational waves is subtly woven in, maintaining momentum while avoiding repetition. 35th insight: gravitational waves, the silent orchestra of cosmic acceleration. For centuries, astronomers relied on light to decode the universe, but now we're learning to listen to its hidden symphony. Gravitational waves, the ripples in spacetime first detected in 2015, aren't just echoes of colliding black holes or neutron stars. They could be the missing link in our hunt for nature's ultimate particle accelerators. Imagine a cosmic thunderclap, a gravitational wave, followed by a downpour of high-energy particles. That's the revolutionary idea gaining traction. Some of the universe's most violent mergers might double as invisible particle slingshots, flinging matter to extreme speeds while warping the fabric of space itself. Take the historic merger of two neutron stars witnessed in 2017. While telescopes caught the accompanying glow of gamma rays and kilonova fireworks, something subtler might have been at work. The collision's unimaginable forces could have twisted magnetic fields into temporary particle accelerators, ejecting cosmic rays too faint to notice at the time. Future observatories like the Einstein Telescope or space-based LISA aim to catch these events earlier and with far greater precision, potentially spotting gravitational wave signals that align with sudden spikes in cosmic ray detectors. It's like matching a fingerprint to a crime scene. The waves tell us where and when to look for hidden acceleration, but the real breakthrough lies in the unknown. Not all gravitational waves come with flashy electromagnetic counterparts. Some might be dark mergers, black holes or neutron stars colliding in near-empty voids, emitting no light but possibly still accelerating particles through sheer gravitational fury. If detectors catch a wave from one of these events and observatories record an unexplained cosmic ray surge from the same patch of sky, it could reveal acceleration mechanisms we've never imagined. This isn't just about adding another tool to our cosmic toolbox. It's about rewriting the rules of detection. For the first time, we're not just observing the universe's violence, we're feeling its tremors and tracing its fallout, piecing together how energy transforms across the spectrum of existence. And as gravitational wave astronomy matures, we might finally answer a question that's haunted physics for decades. What orchestrates the universe's most powerful particle launches? The answer could be hiding in plain sight, not in the light, the particles, or even the waves alone, but in the harmony between them. Because when the cosmos composes its grandest explosions, it doesn't just play one note. It performs a symphony, and we're only just learning to hear the full score. Closing the cosmic chapter, but the story's far from over. We've traveled from the violent hearts of black holes to the ghostly whispers of quantum foam, uncovering a universe that doesn't just allow extreme particle acceleration, it thrives on it. These 35 revelations paint a staggering picture. Cosmic accelerators aren't exceptions to the rules of physics. They are the rules written in magnetic storms, shock waves, and spacetime's hidden wrinkles. Yet for every mystery solved, like how pulsars act as cosmic ratchets or why dark matter might be an invisible architect, a dozen new questions erupt. What's exhilarating is how much lies ahead. Next-generation telescopes, AI-driven analysis, and even gravitational wave detectors are peeling back layers of the cosmos we've never seen. The anomalies we can't yet explain, those ultra-high-energy cosmic rays that defy limits, or the eerie antimatter surplus, aren't dead ends. They're breadcrumbs leading to deeper truths, waiting for a sharper lens or a brighter idea to reveal them. This isn't just a story about particles, it's about ingenuity, the universe's and ours. Every time we decode a piece of the cosmic accelerator puzzle, We're not just learning how matter moves, we're uncovering how everything connects, from the smallest quantum flutter to the largest structures in the cosmos. If this journey through cosmic mysteries left you as awestruck as it did us, don't let the conversation end here. Drop a like if you're hungry for more deep dives, subscribe to stay updated on the next frontier, and shout your wildest space theories in the comments. The universe is whispering its secrets. Together, we'll learn to listen. Until then, keep your eyes on the skies and your mind open to the impossible. Because in this cosmos, the impossible has a way of becoming ordinary. End screen. Call to action overlay for subscription, with visuals of a pulsar jet and a closing shot of the Milky Way.